Today, we are going to be deriving Kepler's second law. Now, what Kepler's second law basically is it states that a planet covers equal areas in equal times. So, as a planet moves along its orbital path, that planet is going to cover equal areas in equal times. Now let me show you what this looks like. So I'm going to say I have the orbital path of a planet right here. So I'm going to say we have the orbital path of a planet that looks like this, right? It's an ellipse. What I'm going to do is I'm going to put the star right here, right? So this is the star that the planet orbits around. Now, there are points when the planet is at this position, and this position, and this position. All right? I'm going to call this position A, B, C, and D. All right. Next what I'm going to do is I'm going to draw lines connecting those planet positions to the star. All right. So we've done this. Now, when I say the area that the planet covers, I'm talking about, okay, so as the planet moves from position A to position B, the planet will have covered this amount of area on its orbital path. And as the planet moved from position C to position D, the planet will have covered this area. All right. Now, if the time it takes for the planet to go from position A to position B is equal to the time it takes for the planet to go from position C to position D, then the area that it covered from this position to this position is equal to the area it covers from this position to this position, right? A planet covers equal areas in equal amounts of time, right? That is what Kepler's second law states. Now, how can we show that this statement is true? Now, if this statement is true, then that means the rate at which a planet covers area with respect to time has to be a constant value. So that means the derivative of the area covered with respect to time has to be a constant value, right? So the amount of area that a planet is covering is increasing at a constant rate. So, how can we show that this statement is true? Now, first, what I'm going to do is I'm going to basically write what this area would be. Now, to do this, I'm going to treat the orbital path of the planet as a polar curve, where the star is the origin of our polar curve, right? So in this case, we have the x-axis and the y-axis, and so the star is our origin. We're integrating from this angular position of the planet to this angular position of the planet, right? This area of the polar curve. So we'll say that this is the initial angular position and this is the final angular position. And we know that the distance from the star to any position of the planet from A to B would just be r, right? And so that's how we would set up the polar curve. Now, we know that the area of a polar curve from one angular position to another is just going to be the integral from the initial angular position to the final angular position of 1/2 r squared d theta. I can make another video showing that this is true in the future, but right now, I'm just assuming that you know what this is. Okay, and so we can write A as dA by just simply saying that this is the same thing as dA equals 1/2 r squared d theta. And you can confirm that this would be true as well by just integrating both sides, right? So, next thing I'm going to do is I'm going to divide dt on both sides because that's how we get the dt in there. So when we're dividing dt, that basically means we're dividing a really small change in time on both sides. So that means we get dA over dt is equal to 1/2 r squared times omega, where we know omega is just d theta over dt, right? The derivative of the angular position with respect to time. Okay. Now I'm going to rewrite this, because notice how I can easily rewrite this as r squared omega all over 2, right? I'm going to rewrite this as that. So in order to prove that dA over dt is constant, I'm going to find a way to show that the numerator is constant and the denominator is constant. Now, if I were to multiply both the numerator and denominator by the mass of the planet, then what we get is we get dA over dt is equal to, so mr squared omega is just going to be the angular momentum of the planet, right? Remember, the angular momentum of the planet will equal mr squared times omega. And in the denominator, we have 2m. Now, we know that the mass of the planet is going to be constant, so the denominator is constant. But how do we know that the angular momentum of a planet is constant? Now, what I'm going to do is I'm going to show you why the angular momentum of a planet is constant. So if the angular momentum is a constant value, then that means the rate at which the angular momentum changes with respect to time has to be equal to 0, right? Because the angular momentum can't change because it's constant, right? Now, we know that the rate at which angular momentum changes is just equal to the torque acting on the object. So what I'm going to try and do is I'm going to figure out what the torque is acting on the planet. So I'm just going to quickly redraw just the star and the planet right here. So, right, any position. Now we know that the torque acting on an object is just equal to Fr sine theta, where we have basically the magnitude of the force vector times the magnitude of the position vector, right, the distance from the star to the planet, times the sine of the angle between the force vector and position vector. So let's see what the force and position vector would look like for the planet. Now, the position vector of the planet would just be a line drawn from the star to the planet. Now, the force vector would be the force acting on the planet, which is directed towards the star. So we have our position vector and we have our force vector. And of course, this force acting on the planet would be gravity. So, notice how the angle between the force vector and the position vector is 180 degrees, right? So the angle between them is 180 degrees. So I can replace theta with 180 degrees. Now, we know that the sine of 180 degrees is equal to 0. So if we multiply this thing by 0, we get that the torque is equal to 0. So the torque is equal to 0. And we know that if the torque is equal to 0, then that means dl over dt has to be 0. If dl over dt is 0, then that means L is a constant value. So this means that L is constant. So the angular momentum of the planet is indeed constant. So we know that, of course, the denominator of L over 2m is going to be constant because the mass of the planet can be assumed to be constant. And we just figured out that the angular momentum of the planet is constant. And that ultimately means that dA over dt, right? dA over dt is indeed a constant value. What does this mean? It means that the rate at which the planet covers area in a certain amount of time is going to be a constant value. So the amount of area that the planet is covering is increasing at a constant rate. And so that means that a planet does indeed cover equal areas in equal amounts of times. And so this verifies Kepler's second law.